In August of 2022, NASA released an audio recording that quickly captured the attention of millions. A sound so unusual that people around the world paused to listen. It wasn't created by musicians or artists or sound engineers imagining what space might sound like. It was real data, translated into something human ears could perceive. Captured from a source over 200 million light-years away. The sound came from a supermassive black hole, and it had been reverberating through a galaxy cluster for longer than complex life has existed on Earth. You're listening to The Drowsy Astronaut, where tonight we explore one of the strangest discoveries in modern astronomy. A black hole that has been producing sound waves for over 2 billion years, screaming into the cosmos in frequencies so deep that no ear could ever detect them naturally. Long before Earth had forests or animals, long before complex life existed at all, those waves were already moving quietly through the surrounding galaxy. Wherever you happen to be listening from tonight, whether the hour is late or the evening is just beginning, just know that you can have a moment of calm and wonder here. This is a 2-hour journey that unfolds slowly, without any rush, so you can drift through the cosmos after a long, hectic day. And if this kind of content helps you unwind, a like or subscribe genuinely helps the channel continue. Whenever you're ready, let us begin. The sound itself, when you hear it, is unlike anything terrestrial. It rises and falls in an oscillating drone, deep and resonant, with a quality that some listeners have described as mournful or even sinister. Others have compared it to a mechanical breathing, something vast and slow and ancient, drawing breath across timescales that dwarf human comprehension. The frequencies shift and move, creating an atmosphere of something immense, operating in darkness far from any observer. What makes this recording remarkable is not merely that it sounds eerie, but that it represents an actual physical phenomenon happening in real time at the heart of a distant galaxy cluster. The black hole is not making sound in the way a speaker produces audio, or an instrument vibrates air molecules in a room. It is generating pressure waves that travel through the superheated gas surrounding it. Ripples of compression and expansion that propagate outward, like waves spreading from a disturbance in water. These pressure waves are, by any physical definition, sound. The source is a supermassive black hole at the center of the Perseus galaxy cluster, one of the largest structures in the known universe, a vast collection of thousands of galaxies, bound together by gravity. The central black hole contains the mass of hundreds of millions of suns, compressed into a region of space smaller than our solar system. This monster does not sit quietly at the center of its domain. It feeds on surrounding material, and as it feeds, it produces jets of energy that blast outward and collide with the gas that fills the cluster. The frequency of the sound this black hole produces is almost incomprehensible. The note is 57 octaves below middle C on a piano, which means the frequency is so low that one complete oscillation of the wave takes roughly 10 million years. A single vibration, one back and forth cycle of the pressure wave, occurs once every 10 million years. This is the deepest note ever detected in the universe, so far beneath human hearing that no biological ear could ever perceive it directly. To put this in perspective, the lowest sounds humans can typically hear are around 20 Hz, meaning 20 vibrations per second. The sound from the Perseus black hole vibrates approximately once every 300 quadrillion seconds. The ratio between what we can hear and what the black hole produces spans a range so vast that normal language fails to capture it. This is why scientists had to shift the frequency upward by 57 octaves before creating the audio that NASA released, multiplying the original frequency by factors of hundreds of quadrillions. The fact that such a low-frequency sound exists at all reveals something profound about the scale of the universe and the processes operating within it. On Earth, sounds are fleeting events, produced by objects vibrating at frequencies that complete many cycles per second. In the vast expanses of galaxy clusters, where distances are measured in millions of light years and time unfolds across billions of years, sound can operate on scales that match the environment. The black hole has been producing these waves continuously, and they have been spreading through the cluster gas for over 2 billion years. The Perseus galaxy cluster itself lies approximately 240 million light-years from Earth, meaning the light and other radiation we detect from it began its journey when dinosaurs still roamed our planet and would not go extinct for another 170 million years. The cluster is enormous by any standard, containing hundreds of galaxies and vast amounts of hot gas that fills the space between them, glowing in X-rays at temperatures of tens of millions of degrees. This gas is the medium through which the sound waves travel. The discovery that black holes could produce actual sound waves came as a surprise to many, because the popular understanding holds that space is silent. This understanding is correct for the emptiness between stars, where the vacuum prevents any pressure waves from propagating. But galaxy clusters are not empty. The gas that pervades them, though incredibly thin by earthly standards, is dense enough for sound to travel at speeds of roughly 1 million miles per hour. The waves move slowly compared to the distances involved, but move nonetheless. The recording NASA released translated this ancient phenomenon into something human senses could perceive, bringing a distant cosmic process into immediate experience. The translation involved not just shifting the frequency, but also mapping different parts of the data to create a sense of the sound moving and evolving. The result is an audio experience that carries real information about what is happening at the center of the Perseus cluster, even though the frequencies have been altered beyond recognition. Some listeners found the sound deeply unsettling, a reminder of the alien nature of the cosmos and the strange processes occurring far from any human presence. Others found it beautiful in its strangeness, an example of science revealing hidden aspects of reality that art alone could never have imagined. The scientific community had known about the sound waves in Perseus for nearly 2 decades before the sonification brought them to public attention. The phenomenon was discovered in 2003 through observations with the Chandra X-ray Observatory, but the technical papers describing the finding remained known primarily to specialists. The sonification project demonstrated that the same data could be communicated in entirely different ways, reaching audiences who would never read an astrophysical journal, but who responded immediately to the experience of hearing. The black hole continues producing these waves at this moment, generating new pressure disturbances that will propagate through the cluster gas for billions of years into the future. The sound we can translate into audio today represents waves that began their journey when the universe was only about 11 billion years old. Before the Sun existed, before the Milky Way had reached its current form. The black hole has been singing this same low note throughout all subsequent cosmic history, and it shows no signs of stopping. The implications of this discovery extend beyond the immediate strangeness of the phenomenon to fundamental questions about how black holes interact with their environments and how energy flows through the largest structures in the universe. The sound waves are not merely an interesting curiosity, but a mechanism through which the black hole influences its surroundings, transferring energy across vast distances and affecting the evolution of the entire cluster. We will explore these implications as the night continues. The fact that we can now hear this process, even in translated form, represents a new way of experiencing the universe that complements the visual observations that have dominated astronomy throughout its history. The cosmos has been singing all along in frequencies and on timescales that our brief lives could never directly perceive. But we have developed tools that extend our senses, instruments that detect what eyes cannot see, and techniques that translate the inaudible into sound. The black hole's scream becomes accessible. The night stretches on, and we have only begun exploring this phenomenon. The sound from Perseus invites us to consider what else might be singing in the universe. What other processes produce waves that ripple through media we have not yet learned to listen to? The deepest note ever detected is also an invitation to listen more carefully to a cosmos that has been vibrating with activity since the beginning of time. The common understanding that space is silent rests on a fundamental truth about how sound works, requiring a medium through which pressure waves can travel. In the vacuum between stars, where atoms are so sparse that they almost never collide, no such medium exists. If you floated in interstellar space and screamed, no one could hear you, because there would be nothing to carry the vibrations from your mouth to their ears. This basic physics has been repeated so often that it seems absolute. But the universe is not uniformly empty. Between the galaxies and a cluster like Perseus lies hot gas that was heated to extreme temperatures during the cluster's formation and remains suspended there by gravity. This gas is incredibly thin by earthly standards. A volume of space that would fit comfortably in your living room might contain only a few atoms. Yet across the scales of a galaxy cluster, even this tenuous material adds up to enormous quantities. Enough to outweigh all the stars in all the galaxies the cluster contains. The atoms and ions that compose it collide with each other, and when a disturbance compresses one region, that compression propagates outward as neighboring particles bump into each other and pass the disturbance along. The process is exactly analogous to sound traveling through air, only stretched across distances measured in millions of light years and occurring over timescales measured in millions of years. The physics is identical, only the parameters differ. What NASA released in 2002.2 is not a simulation or an artistic interpretation of what scientists imagine a black hole might sound like. The audio represents actual pressure waves detected through careful observation, translated into frequencies humans can hear. The underlying phenomenon is genuinely acoustic in nature. The black hole is producing real sound, traveling through real gas, carrying real energy across real distances. The detection of these waves came through observations of X-ray emissions from the hot cluster gas. The Chandra X-ray Observatory produced images showing the gas distribution, and in these images, scientists noticed concentric ripples spreading outward from the central black hole. These ripples represent regions where the gas is slightly denser or less dense than its surroundings. Exactly what you would expect from sound waves propagating through a medium. By measuring the spacing between the ripples and understanding the properties of the gas, its temperature, density, and composition, scientists could calculate the wavelength and frequency of the waves. The wavelength turned out to be enormous, with individual ripples spanning tens of thousands of light years. The frequency was correspondingly low, with each complete oscillation taking roughly 10 million years to complete. This is the fundamental note the black hole has been playing. The translation process that produced the NASA audio involved several steps, each designed to preserve the essential character of the data while making it accessible to human perception. The first step was shifting the frequency upward by 57 octaves, which means multiplying the original frequency by 2 raised to the 57th power. This enormous factor brings the vibrations into the range where human ears can detect them, transforming oscillations spanning millions of years into oscillations lasting fractions of a second. The second step involved mapping the spatial distribution of the sound around the black hole into something that could be played as audio changing over time. The original data is a snapshot, an image showing ripples frozen at a particular moment. The sonification turned this into a time-evolving sound by scanning across the image, playing different parts of the data in sequence to create the sense of the sound moving and breathing. The result is the audio that captured public attention. A deep, oscillating tone that rises and falls with an unsettling quality that many listeners found memorable. The specific character of the sound reflects actual variations in the data. Regions where the ripples are more or less intense, areas where the gas density changes in particular patterns. The haunting quality is not invented, but emerges from the translation of real physical variations. The gas through which these sound waves travel exists at temperatures of tens of millions of degrees, far hotter than the surface of the sun. At these temperatures, the gas is fully ionized, meaning the electrons have been stripped from atoms, leaving a plasma of charged particles. Despite these extreme temperatures, the gas is so thin that if you could somehow stand in it, you would freeze rather than burn, because the energy transfer rate would be too low to warm you significantly. The heat is real but diffuse. Sound travels through this hot plasma at speeds much higher than sound travels through air on Earth. Roughly 1 million miles per hour, compared to roughly 700 miles per hour for sound in our atmosphere. This higher speed reflects the higher temperature, since sound speed depends on how fast particles are moving on average. Even at 1 million miles per hour, however, the distances are so vast that the waves take millions of years to propagate across the cluster. The detection of actual sound waves in galaxy cluster gas represented a significant confirmation of theoretical predictions about how energy from central black holes influences their environments. The waves carry energy outward, heating the gas and preventing it from cooling and collapsing. This process, discovered through the sound waves themselves, turns out to be crucial for understanding how galaxies evolve within clusters. The reality of the sound also raises questions about what else might be vibrating in the cosmos that we have not yet learned to detect. If supermassive black holes in galaxy clusters produce sound waves, what about smaller black holes in less dense environments? What about the violent events that occur when galaxies collide or when supernovae explode? The universe may be filled with acoustic phenomena, operating on scales and at frequencies we have only begun to explore. The sonification project that produced the Perseus audio was part of a broader NASA initiative to translate astronomical data into sound, exploring how non-visual representations might reveal patterns or reach audiences that images alone could not. The Perseus black hole became the most famous example because the sound was so striking and because the phenomenon it represented was so genuinely alien. But the project has produced many other sonifications, each translating different types of data into different audio experiences. The bottom line is that what you hear in the NASA recording is not fiction or metaphor, but physics made audible. A black hole, 240 million light-years away, has been generating pressure waves for over 2 billion years, and we have figured out how to translate those waves into something human senses can perceive. The universe speaks in frequencies we were never evolved to hear, but we have developed tools to listen anyway. The medium through which the sound travels, the hot cluster gas, is itself a subject of intense study, representing most of the ordinary matter in galaxy clusters. This gas fell into the cluster's gravitational well over billions of years, heated by compression and by energy from galaxies and black holes within. It glows brightly in X-rays, making it visible to instruments like Chandra, and its properties can be measured with considerable precision through spectroscopic analysis. The interaction between the central black hole and this gas determines much of the cluster's evolution over cosmic time. Without the energy input from the black hole, the gas would cool, condense, and form stars at rates far higher than observed. The sound waves are part of the mechanism that prevents this cooling, carrying energy outward and keeping the gas hot. The physics connects the smallest scales of the black hole to the largest scales of the cluster. The distinction between the vacuum of empty space and the gas-filled environment of galaxy clusters is crucial for understanding why sound exists in one context and not the other. The universe contains vast, empty regions where no sound could ever propagate. But it also contains regions where gas is present and pressure waves can travel. The Perseus cluster happens to be one of the best studied examples of the latter, its central black hole providing a powerful source, and its gas providing a medium for detection. The original frequency of the sound waves from the Perseus black hole is so far beneath human hearing that describing it requires analogies that strain intuition. A single vibration, one complete cycle of compression and expansion in the cluster gas, takes approximately 10 million years to complete. If you could somehow wait for one oscillation of this sound, entire species would evolve and go extinct on Earth before the wave finished its cycle. This is not slow music, this is vibration on geological and astronomical timescales. Human hearing spans roughly 10 octaves, from the deepest bass notes we can perceive at around 20 Hz to the highest frequencies around 20,000 Hz. Below 20 Hz, vibrations become infrasound, felt more than heard, experienced as pressure rather than tone. The black hole's frequency lies so far below even infrasound that the comparison becomes almost meaningless. Billions of times lower than anything any ear could detect. Waves that make the deepest whale songs seem like ultrasonic squeaks. To bring this into audible range, scientists had to shift the frequency upward by 57 octaves. Each octave represents a doubling of frequency, so shifting by 57 octaves means multiplying by 2 to the 57th power. This is approximately 140 quadrillion, a number so large that writing it out would require 18 digits. The translation compressed 10 million years of vibration into fractions of a second. The sonification process did not merely shift the frequency, but also had to map spatial information into temporal information, turning a static image of ripples into a dynamic audio experience. The Chandra observations produced maps showing where the gas was denser and where it was less dense, concentric patterns spreading outward from the central black hole. These maps represent a frozen moment, not a recording of sound over time. The challenge was to translate this snapshot into something that would sound like evolving audio. The solution involved scanning across the data, playing different parts of the image as audio samples arranged in sequence. Imagine running your finger across a textured surface and feeling the bumps translate into a series of sensations. The sonification did something similar, converting spatial variations into temporal variations. The ripples in the X-ray image became the oscillations in the audio, with regions of higher density producing louder or different tones. The direction of the scan affects the character of the resulting sound, and the NASA team experimented with different approaches before settling on the version they released. Scanning outward from the center toward the edges creates a sense of the sound expanding, matching the actual physics of waves propagating away from their source. Different scanning directions would produce different audio experiences, though all would represent the same underlying data. The frequency shifting was accomplished through a process similar to how musicians transpose music to different keys, though on a vastly more extreme scale. The original data specifies how the gas density varies across space, which corresponds to how the pressure wave compresses and expands the medium. This spatial pattern was converted to a time series, and the time series was sped up by the 57-octave factor to bring it into audible range. The resulting audio maintains the proportional relationships in the data, even though the absolute frequencies are completely different. The specific frequency chosen for the audible version was not arbitrary but was selected to place the sound in a range where human hearing is sensitive and where the character of the oscillations would be clearly perceptible. Too low, and the sound would feel like rumbling rather than a discernible tone. Too high, and the quality of the sound would change in ways that might obscure the underlying patterns. The 57-octave shift landed the audio in a bass range that felt appropriate for representing something so massive and slow. Additional processing was applied to make the audio more listenable without distorting the scientific content. The raw translation produced sound, but adjustments to dynamics and equalization helped bring out details that might otherwise be masked. The goal was not to make the audio pretty, but to make it accurately represent the data while being accessible to listeners without specialized training. The result of all this processing is the audio clip that spread across the internet in 2022. Roughly a minute of deep, oscillating sound that rises and falls with an almost biological quality. Listeners often describe feeling the sound as much as hearing it, even through normal speakers, because the frequencies are low enough to move air in ways that affect more than just the eardrums. The experience is physical as well as auditory. The variations in the audio reflect real variations in the X-ray data. Regions where the ripples are more pronounced, producing louder or more distinct tones. The overall rising and falling quality comes from the fact that the ripples are concentric, with the intensity varying as the scan moves through different parts of the pattern. What sounds like breathing or pulsing in the audio corresponds to the alternating rings of compression in the cluster gas. The scientific content of the sonification is genuinely there, preserved through the translation process, in ways that allow researchers to potentially hear patterns they might miss in visual representations. The human auditory system evolved to detect subtle variations in timing and frequency, skills that helped our ancestors locate prey and predators. These skills can be applied to astronomical data when that data is presented in audio form, potentially revealing patterns that graphs and images might not make obvious. Sonification as a scientific technique has grown in sophistication and acceptance over recent years, moving from a novelty used primarily for public outreach to a legitimate analysis tool used by researchers. The Perseus black hole sonification demonstrates both applications. It engaged millions of non-specialists while also providing a new way to experience data that scientists have studied for decades. The two purposes are not in conflict. Making data accessible often reveals its richness in new ways. The choice to release the Perseus audio as part of Black Hole Week in August 2022 reflected NASA's understanding that the sound would capture public imagination in ways that images and technical descriptions might not. The timing was deliberate, the presentation was carefully crafted, and the result exceeded expectations. The audio became one of the most shared pieces of scientific content that year, reaching audiences who might never engage with X-ray astronomy otherwise. The technique of extreme frequency shifting raises interesting questions about what is preserved and what is lost in such translations. The proportional relationships in the data survive. Regions that were twice as dense produce sounds that are correspondingly different, but the absolute frequencies are completely transformed. Whether the audio still counts as the same sound is a philosophical question. What is certain is that it represents the same physical phenomenon, translated for human perception. The accessibility of sonified data extends beyond casual listening to include researchers who are blind or visually impaired, for whom traditional astronomical imagery presents obvious barriers. Sonification provides an alternative pathway to the same information, allowing these scientists to engage with data on equal footing with their sighted colleagues. The Perseus audio is part of a broader movement toward making astronomy more inclusive through diverse representations. The emotional impact of the audio should not be dismissed as unscientific or separate from the intellectual content. Humans are emotional beings, and the feelings evoked by hearing the black hole, awe, unease, wonder, perhaps fear, are legitimate responses to encountering something genuinely alien and vast. Science that only engages the intellect reaches only part of what makes us human. Science that also evokes feeling creates deeper connections and longer-lasting impressions. The process of making the inaudible audible is ultimately an act of translation, Like rendering a text from one language to another, something is always lost in translation, but something is also gained. Accessibility to those who did not speak the original language. The Perseus black hole spoke in frequencies no ear could hear, across timescales no life could experience. The sonification translates that alien voice into something we can perceive, an act of bridging that is both technically impressive and humanely significant. The Perseus galaxy cluster stretches across millions of light-years of space, one of the most massive structures within a few 100 million light-years of Earth. To call it large understates the case dramatically. The cluster contains over 1,000 galaxies, each home to billions of stars, all bound together by gravity into a single enormous structure. The hot gas that fills the space between these galaxies contains more ordinary matter than all the galaxy's stars combined. This is the environment where the black hole sings. At the center of the cluster lies its dominant galaxy, designated NGC 1275, a giant elliptical galaxy that has grown to enormous size by swallowing smaller galaxies over billions of years. Unlike spiral galaxies like our Milky Way, which have defined structures of arms and disks, elliptical galaxies are more amorphous collections of stars, their shapes smoothed by countless gravitational interactions. NGC 1275 is among the largest galaxies known, its stellar population numbering in the trillions. At the very center of this giant galaxy sits the source of the sound, a supermassive black hole with a mass of approximately 800 million times that of our Sun. This is not the largest supermassive black hole known, but it is still almost incomprehensibly massive, containing more matter than most galaxies' worth of stars, compressed into a volume smaller than our solar system. The event horizon, the boundary beyond which nothing can escape, spans roughly 16 billion kilometers. A black hole of this size does not simply sit passively at the center of its galaxy. Material from the surrounding environment falls toward it constantly, drawn by gravity so intense that nothing can resist. This infalling material does not plunge straight in but spirals around the black hole, forming a flattened disk of superheated gas that glows with tremendous intensity. The gravitational energy released as matter falls inward powers some of the most energetic phenomena in the universe. The material closest to the black hole reaches temperatures of billions of degrees and velocities approaching the speed of light. Not all of this material falls into the black hole. Some of it gets funneled into narrow jets that blast outward from the black hole's poles at relativistic speeds, carrying enormous amounts of energy into the surrounding environment. These jets are the immediate source of the sound waves we detect, the mechanism by which the black hole's fury translates into pressure waves in the cluster gas. The jets punch through the gas that surrounds the galaxy, plowing outward like cosmic snowplows clearing paths through the medium. Where the jets meet the cluster gas, shock waves form, and behind the shocks, enormous cavities inflate, bubbles of relativistically hot plasma that displace the surrounding material. These bubbles are visible in X-ray images as dark regions against the bright background of the cluster gas, voids where the jets have cleared the material away. The black hole at the center of NGC 1275 has been classified as a type of active galactic nucleus, though its activity level is considered moderate compared to the most violent examples. Active galactic nuclei range from quasars, which outshine entire galaxies, to more subdued sources like the Perseus black hole, which emits energy at rates millions of times higher than the Sun, but still far below the most extreme cases. The technical classification is a Seyfert galaxy with radio jets. The feeding rate of the black hole determines its activity level, with more material falling in producing more energetic output. The Perseus black hole is currently in a relatively steady state, consuming material at a rate that produces persistent jets without the dramatic variability seen in some active galaxies. This steadiness may be why the sound waves are so regular, why the ripples in the cluster gas form such neat concentric patterns rather than chaotic disturbances. The relationship between the black hole and its host galaxy has evolved over billions of years, with the black hole growing as it consumed material, and the galaxy growing as it merged with smaller systems. The current configuration represents a mature stage of this evolution, with the black hole and galaxy having reached a kind of equilibrium. The energy the black hole injects into the cluster gas through jets and sound waves affects how the galaxy itself can grow, creating a feedback loop that regulates both. The mass of the black hole, 800 million solar masses, places it in the upper range of supermassive black holes, but below the largest known examples. The most massive black holes discovered to date contain tens of billions of solar masses, found at the centers of the largest galaxies in the largest clusters. These monsters are rare, but they demonstrate that black holes can grow to almost any size given enough time and enough material to consume. The physics operating near the event horizon of such a massive black hole is governed by general relativity, Einstein's theory of gravity that describes how mass warps space-time. Near the black hole, this warping becomes extreme, bending light into curved paths and slowing time relative to distant observers. Objects falling toward the event horizon appear to freeze as they approach, their light red shifting into invisibility as they cross the boundary from which no return is possible. The jets that produce the sound waves originate from the region just outside the event horizon, where magnetic fields, twisted by the rotating disk of infalling material, funnel some of the gas outward at tremendous speeds. The exact mechanism that produces jets is still debated, with different models proposing different configurations of magnetic fields and different connections to the black hole's spin. What is clear is that jets require the extreme environment near a black hole to form. The energy carried by the jets ultimately comes from gravity, from the potential energy released as matter falls toward the black hole. This gravitational energy conversion is extraordinarily efficient, far more so than nuclear fusion in stars. A significant fraction of the mass of infalling material gets converted to energy before that material crosses the event horizon, powering the jets and other emissions. This efficiency is why active galactic nuclei can be so luminous despite their compact sizes. The Perseus black hole is relatively nearby as active galactic nuclei go, allowing detailed study that more distant examples do not permit. The proximity of 240 million light-years sounds vast by human standards, but is modest in cosmological terms. More distant active galaxies appear as points of light, even in the most powerful telescopes, while Perseus can be resolved into detailed maps showing the ripples and cavities that the black hole has created. The continued activity of the black hole ensures that new sound waves are being generated constantly. New jets punching into the gas, new bubbles inflating, new pressure disturbances propagating outward. The waves we detect today were generated over 2 billion years ago, but the black hole has not been idle since. It has been producing new waves continuously, waves that will reach our instruments millions of years in the future, if any instruments still exist to detect them. The monster at the center of Perseus is both destructive and creative, consuming matter while simultaneously shaping the environment around it in ways that affect millions of light years of space. The jets and bubbles and sound waves are all aspects of this shaping, mechanisms through which the black hole's energy spreads outward and influences structures far beyond the galaxy it inhabits. The black hole is not merely a drain, it is a force that actively sculpts the cosmos. The visualization of such a black hole requires imagination, because no image can truly capture what a supermassive black hole looks like. The famous image of M87's black hole, released in 2019, shows only the shadow of the event horizon against a glowing ring of surrounding gas. The Perseus black hole has not been imaged this way, though it could be a future target for the Event Horizon Telescope. What we see instead are its effects. The ripples, the bubbles, the sound it makes. The journey from the black hole at the center to the ripples in the cluster gas spans enormous distances, with the jets extending for tens of thousands of light years and the bubbles reaching hundreds of thousands. The sound waves propagate even farther, filling much of the cluster with their low-frequency vibrations. The influence of this single object, smaller than our solar system, extends across volumes that dwarf entire galaxies. The mechanism by which the Perseus black hole generates sound waves involves a chain of processes that connects events near the event horizon to disturbances felt millions of light years away. The chain begins with material falling toward the black hole, continues through the formation and propagation of jets, and culminates in pressure waves spreading through the cluster gas. Each step transforms energy from one form to another, ultimately producing the acoustic phenomenon we have learned to detect. As gas spirals toward the black hole, it forms an accretion disk, a flattened structure where material orbits faster and faster as it approaches the center. Friction within the disk heats the gas to extreme temperatures and causes it to slowly spiral inward, losing orbital energy as it goes. The innermost regions of the disk glow brightly in X-rays, producing some of the most energetic radiation in the universe. This accretion process powers everything that follows. Some fraction of the infalling material does not cross the event horizon, but instead gets launched outward in the form of jets. These jets emerge perpendicular to the accretion disk, blasting away from the black hole's poles at speeds approaching the speed of light. The exact mechanism that produces jets involves magnetic fields anchored in the accretion disk, and possibly the spinning black hole itself, twisted and wound up until they channel material outward with tremendous force. The jets carry enormous amounts of energy, far more than the radiation emitted by the accretion disk. As they travel outward through the surrounding gas, they plow through the medium like cosmic battering rams, pushing material aside and creating shock waves at their leading edges. The gas that gets pushed aside does not simply disappear. It piles up at the boundaries of the jets, forming dense shells around the cleared channels. Behind the shocks, where the jets have cleared paths through the medium, enormous cavities form. These bubbles of relativistically hot plasma contain particles accelerated to tremendous energies, trapped by magnetic fields and radiating at radio wavelengths. The bubbles are not empty, but are filled with material so hot and tenuous that it appears dark against the X-ray emitting cluster gas. They can grow to enormous sizes, spanning tens of thousands of light years. As the bubbles expand, they push against the surrounding gas, compressing it and creating disturbances that propagate outward. This is where the sound begins. The expanding bubbles act like speakers, their inflation creating pressure waves that travel through the cluster gas in all directions. The frequency of the waves depends on how quickly the bubbles expand and how often new bubbles form, which connects to the activity cycle of the central black hole. The Chandra X-ray Observatory revealed these pressure waves as visible ripples in images of the Perseus cluster, concentric rings of slightly higher and lower density spreading outward from the center. The ripples are subtle, representing variations of only a few percent in the gas density, but they are clearly present in deep observations that accumulate photons over many hours. The pattern looks almost like ripples spreading from a stone dropped in water, frozen at a single moment in time. By measuring the spacing between the ripples and knowing the properties of the gas through which they travel, scientists could calculate the wavelength and frequency of the waves. The wavelength is enormous, roughly 30 to 6,000 light years from one compression to the next. The frequency, which is the speed of sound in the medium divided by the wavelength, works out to one oscillation every 10 million years. This is the deepest note ever measured from any cosmic source. The ripples visible in X-ray images extend outward for hundreds of thousands of light years, tracing the path of sound waves that have been propagating for over 1 billion years. The innermost ripples are the youngest, produced most recently by the ongoing activity of the black hole. The outermost ripples are ancient, generated long ago when the universe was substantially younger. The pattern represents a record of the black hole's activity, written in the cluster gas. The energy carried by these sound waves is substantial, enough to heat the cluster gas and prevent it from cooling and collapsing. Without this energy input, the gas would radiate away its thermal energy in X-rays, cool to lower temperatures, and eventually condense to form new stars at rates far higher than observed. The sound waves keep the gas hot, serving as the mechanism for the heating that prevents overcooling. This connection to galaxy evolution makes the sound waves scientifically important, not just acoustically interesting. The calculation of how much energy the sound waves carry involves measuring the amplitude of the pressure variations, the volume through which the waves propagate, and the speed at which they travel. The numbers are impressive. The mechanical energy in the sound waves amounts to roughly 10 to the 44th joules, an incomprehensibly large value that represents the gravitational energy of countless infalling gas clouds converted to acoustic vibrations. This energy accumulated over billions of years. The continuous nature of the process matters for understanding how the heating works. The black hole does not produce a single burst of sound, but rather an ongoing stream of pressure waves that perpetually replenish the energy lost through radiation. The balance between heating by sound waves and cooling by X-ray emission determines the temperature structure of the cluster gas, which in turn affects how galaxies within the cluster evolve. The sound is part of a feedback loop that regulates cosmic structures. The physical analogy to sound production on Earth is apt but imperfect. On Earth, a speaker produces sound by vibrating a membrane that pushes on air molecules, creating pressure waves that propagate outward. The black hole's jets and bubbles serve a similar function, pushing on the cluster gas and creating pressure waves that propagate outward. But the scales are so different that the analogy strains. A speaker vibrates thousands of times per second. The black hole's bubbles expand over millions of years. A speaker's sound travels meters. The black hole's sound travels millions of light years. The detection of these sound waves required understanding both what to look for and where to look for it. The X-ray observations that revealed the ripples were not initially understood as acoustic phenomena. Scientists had to connect the visual patterns in the images to the theoretical prediction that expanding bubbles would create pressure disturbances. Once this connection was made, the interpretation became clear, but reaching that understanding required insight and persistence. The translation of X-ray ripples back into audio closes a conceptual loop, taking a phenomenon that was always acoustic in nature, but visually detected, and returning it to the sensory domain it originated from. The sound was there all along, frozen in the X-ray images as patterns of light and dark. The sonification liberated it from visual representation and restored its acoustic character, allowing us to hear what the black hole has been doing for billions of years. The concentric ripples in the Perseus cluster gas were first noticed in images taken by the Chandra X-ray Observatory in 2002, but their true nature was not immediately recognized. The observers saw patterns in the data, rings of slightly brighter and darker emission, spreading outward from the central galaxy. But what these patterns represented remained uncertain. Several possible explanations were considered before the acoustic interpretation emerged. The initial reaction to the images focused on the cavities, the obvious dark bubbles that the jets had inflated in the cluster gas. These features were dramatic and clearly connected to the active galactic nucleus at the center. The ripples surrounding the cavities were subtler, requiring careful analysis to confirm they were real features rather than artifacts of the imaging process or statistical fluctuations in the data. Their reality was not immediately obvious. One possibility considered was that the ripples were shock waves from explosive events at the center. One-time disturbances that had propagated outward and happened to be caught at this moment. Another possibility was that they represented the edges of multiple generations of bubbles, the piled-up gas from many expansion episodes, creating the ring-like patterns. The acoustic interpretation required recognizing that the ripples had properties consistent with sound waves rather than shocks. The breakthrough came when researchers calculated the properties the waves would need to have if they were indeed acoustic phenomena. Sound waves in a medium travel at a speed determined by the temperature and composition of that medium. The cluster gas temperature was well known from spectroscopic observations, allowing the sound speed to be calculated, roughly 1 million miles per hour. Given this speed and the observed spacing of the ripples, the frequency of the waves could be determined. The numbers pointed to the extraordinarily low frequency that made the finding remarkable. The paper announcing the discovery was published in 2003, presenting evidence that the Perseus cluster gas contained sound waves with frequencies corresponding to B-flat 57 octaves below middle C. The finding was significant within the astrophysics community, but did not reach broad public awareness. The dry language of scientific publication pressure fluctuations, acoustic power, thermal equilibrium, did not convey the strangeness of what had been found in terms that general audiences could connect with. Part of what delayed the discovery's recognition was that sound waves in space contradicted popular understanding so completely that even scientists needed time to adjust. The idea that pressure waves could propagate through the cosmos, that something resembling sound could exist at scales spanning millions of light years, challenged intuitions shaped by the correct but limited statement that space is a vacuum. The Perseus discovery showed that this statement requires qualification. The scientists who made the discovery recognized its significance for understanding how black holes influence their environments, which was their primary interest. The acoustic interpretation connected to the long-standing puzzle of why cluster gas does not cool as quickly as expected. If sound waves carry energy outward and heat the gas, this could explain the puzzle. The discovery was important for understanding cluster physics, not merely for being strange and wonderful. The years between the original discovery and the NASA sonification saw continued research on the Perseus sound waves and on similar phenomena in other clusters. The basic finding was confirmed through deeper observations and more sophisticated analysis. Other clusters were found to show similar ripples, though Perseus remained the clearest example due to its proximity and the strength of its central black hole's activity. The technical literature accumulated papers discussing the mechanics of the waves, the energy they carried, and their role in regulating cluster evolution. None of these papers broke through to popular attention because none translated the phenomenon into terms that non-specialists could experience. The information was there, but it was locked in the specialized language and publication venues of professional astronomy. The NASA Sonification project, when it finally translated the data into audio, nearly 2 decades after the discovery, was not presenting new science, but rather new communication. The phenomenon had been known and studied for years, but it had never been made accessible to the public in a form that could compete for attention against the flood of information people encountered daily. The audio changed that, giving people a direct sensory experience of something previously confined to X-ray images and technical papers. The success of the sonification demonstrated a gap between what scientists know and what the public has absorbed. Discoveries that specialists consider settled and familiar can still be revelations to general audiences who were never exposed to them. The Perseus sound waves had been known to astrophysicists for 2 decades, but to the millions who heard the audio in 2022, they were entirely new. The delay in communication matters. The researchers who made the original discovery could not have predicted that their work would eventually reach millions through an audio translation. They were focused on understanding the physics, not on public engagement. The later decision by NASA to include Perseus in a sonification project reflected changed priorities around science communication and a recognition that data can be shared in multiple forms for different purposes. The delayed understanding of what the ripples represented illustrates how scientific insight sometimes arrives gradually rather than in a single flash of recognition. The observers saw patterns but did not immediately know what they meant. The interpretation required connecting visual data to theoretical models of how sound propagates, a connection that was not obvious until someone thought to make it. The discovery was not instantaneous, but emerged from sustained attention. The gap between discovery and public communication also reflects the specialized nature of modern science. where findings published in technical journals rarely reach broader audiences. Most people do not read astrophysical papers and have no way of learning what they contain unless some intermediary translates and disseminates the information. NASA's sonification project served this intermediary function, bridging the gap between specialists and the public. The 2-decade delay between discovery and sonification may seem long, but it allowed time for the science to mature, for the findings to be confirmed and extended, and for the interpretation to solidify. By 2002, the acoustic nature of the ripples was not controversial. It was established fact. The sonification could be presented with confidence because the underlying science was secure. The story of the discovery reveals something about how knowledge advances and how it eventually spreads beyond specialist communities. The ripples were there to be seen, the data publicly available, but seeing required knowing what to look for and recognizing the significance of what was found. The acoustic interpretation emerged from expertise and insight, not from superior data. Once the interpretation was established, the path to public awareness required a different kind of effort: translation into accessible form. The original discoverers deserve credit for the insight that identified the ripples as sound waves, even though the subsequent sonification by others brought the finding to public attention. Scientific progress often works this way, with foundational work done by researchers who receive little public recognition, while communication efforts by others capture popular imagination. Both contributions matter. Neither would be significant without the other. The discovery that black holes produce sound waves has become part of established astrophysical knowledge, taught in courses and referenced in subsequent research. The sonification ensured that this knowledge also became part of public awareness, reaching audiences who will never take an astrophysics course, but who now know that the universe contains sounds beyond hearing. The dissemination completes the discovery's significance. The pressure waves currently propagating through the Perseus cluster began their journey outward over 2 billion years ago, a span of time so vast that comparison to human experience fails almost completely. When these waves were first generated, the universe was only about 11 billion years old. Stars that now populate the Milky Way had not yet formed. The ancestors of all complex life on Earth were single-celled organisms floating in ancient oceans. Earth itself was a very different place 2 billion years ago, during a geological period called the Paleo-Proterozoic. The atmosphere contained little oxygen, perhaps 2 or 3% compared to today's 21%. Life existed exclusively as microbes, with the first eukaryotic cells, the kind that make up all animals and plants, only just beginning to appear. The great oxidation event had only recently occurred, transforming the atmosphere through photosynthesis. The black hole had been screaming for a long time before anything on Earth could hear. The timeline of the sound waves spans most of Earth's biological history. The waves were generated before the Cambrian explosion that produced the first complex animals. They were traveling through the cluster while fish developed, while plants colonized land, while dinosaurs rose and fell. Human evolution, from the earliest hominids to the present day, occupies less than the final 1% of the time these waves have been propagating. The black hole itself was already ancient when it produced the waves we detect today, having formed and grown over billions of years before even this early period. Supermassive black holes in the centers of galaxies likely formed shortly after the first galaxies themselves, growing through mergers and accretion throughout cosmic history. The Perseus black hole had been active, producing jets and bubbles and sound waves for billions of years before the particular waves we now observe began their journey. The sound waves travel through the cluster gas at approximately 1 million miles per hour, which sounds fast but is modest compared to the distances involved. At this speed, a wave takes roughly 4.5 million years to cross a distance equal to the gap between the Sun and Alpha Centauri, the nearest star system. The waves have been traveling for over 2 billion years, yet they have only spread through a portion of the cluster. The outermost ripples detected are still well within the cluster's boundaries. The journey of these waves is not a single event, but a continuous process. The black hole has been producing new waves constantly throughout the 2 billion years since the oldest detected waves began. Waves generated more recently are closer to the center. Waves generated long ago have spread farther out. The pattern of concentric ripples represents this ongoing production, with each ring corresponding to a different epoch of the black hole's activity. The continuity of the sound over such extended periods suggests that the black hole's feeding and jet production have been relatively steady throughout this time. Dramatic variations in activity would produce irregular wave patterns, gaps or intensifications that the observations would reveal. The regular spacing of the ripples indicates consistent energy output over billions of years, a remarkably stable process operating at the heart of the cluster. This stability connects to the feedback mechanism that regulates the black hole and its environment. If the black hole's activity decreased, less energy would flow into the cluster gas, allowing it to cool and potentially fall back toward the center. This increased infall would provide more fuel for the black hole, increasing its activity again. If activity increased too much, the energy input would heat the gas and push it outward, reducing the fuel supply and decreasing activity. The balance tends to self-regulate. The 2 billion year timescale of the detected waves is determined by how far they have traveled, divided by their speed, not by when the black hole started producing them. The black hole almost certainly produced earlier waves that have since propagated beyond the region we can observe or have dissipated into the intergalactic medium. The waves we detect are simply those currently within range, a snapshot of an ongoing process. The universe during the epoch when these waves began looked substantially different from today. Galaxies were generally smaller and more chaotic, still assembling through mergers that would produce the large, mature systems we observe now. The cosmic star formation rate was higher, with new stars forming throughout the universe at rates that have since declined. The distribution of galaxies was less organized, with fewer of the large clusters and superclusters that characterize the present cosmos. The Perseus cluster itself was younger, but already substantial, having grown through the gravitational attraction of surrounding matter over the previous billions of years. The central galaxy was smaller than it is now, still in the process of swallowing satellites that would add to its mass. The black hole was less massive too, though already enormous by any ordinary standard. The system was evolving toward its current state. While the sound waves began spreading outward, the light we receive from Perseus today also began its journey long ago, though not as long as the sound waves. At 240 million light-years distant, the light has been traveling since before the dinosaurs went extinct. The images we see show the cluster as it was in the late Paleozoic era, well before the present, but much more recently than the sound waves. The different timescales layer upon each other, with the sound carrying information from an even more distant past. The coexistence of such different timescales in a single observation reveals the complexity of studying distant cosmic objects. The ripples in the X-ray images represent waves that began long ago, but are observed through light that departed more recently. The interpretation requires keeping track of what happened when, connecting phenomena separated by hundreds of millions of years. The cluster we observe is a superposition of different historical epochs. The fact that these waves have been propagating for longer than complex life has existed on Earth creates a kind of existential perspective, a reminder of human smallness against cosmic scales. The black hole's scream began before there were ears anywhere in the universe capable of hearing it, before brains existed that could wonder about it, before hands could build telescopes that could detect it. The phenomenon preceded us and will outlast us. This perspective can be humbling or inspiring depending on how one receives it. The universe does not require human presence to operate, does not need us to validate its processes, exists and evolves independently of whether any observers watch. Yet we have developed the ability to discover and understand these processes, to detect waves produced before our planet had land animals, to translate cosmic phenomena into human experience.
Smallness does not preclude significance.
The waves continue propagating tonight, spreading further through the cluster with each passing moment, carrying energy that was released when the universe was young. New waves are being generated as well, ripples that will not reach the cluster's outskirts for another 2 billion years. The process operates continuously, indifferent to observation, a natural consequence of physics playing out at cosmic scales. The black hole's song has no known beginning and no foreseeable end. It was already singing when the waves we detect were generated, and it continues singing now. The sound fills the cluster volume, pressure variations too low to hear rippling through gas, too thin to touch, carrying more energy than humanity has ever harnessed for any purpose. The song plays on. The sound waves from the Perseus black hole are not merely an interesting curiosity, but a window into processes that determine how the largest structures in the universe evolve over billions of years. The waves carry energy, and this energy influences the behavior of the cluster gas in ways that affect everything from star formation to galaxy growth. Understanding the sound means understanding the feedback loop between black holes and their cosmic environments. The central question the sound waves help answer involves a puzzle that astrophysicists noticed decades ago. The hot gas in galaxy clusters emits X-rays as it radiates energy, and this radiation should cause the gas to cool over time. As it cools, it should condense and fall towards the cluster center, providing fuel for star formation and black hole growth. Yet observations show that this cooling flow is much weaker than expected. Something is heating the gas and preventing it from cooling as rapidly as it otherwise would. The sound waves provide part of the answer. As they propagate through the cluster, they carry energy that was originally released by the black hole's jets. This energy gradually dissipates into the gas, heating it and counteracting the cooling from X-ray radiation. The waves act as a heating mechanism that operates across the entire cluster volume, reaching regions far from the central black hole that would otherwise be too distant to feel its influence directly. The amount of energy carried by the sound waves can be calculated from the properties of the ripples, their amplitude, their spacing, their propagation speed. The calculation yields enormous numbers, roughly equivalent to the energy output of 10 billion suns operating continuously for billions of years. This energy is not concentrated in radiation, but distributed through the mechanical work of pushing gas back and forth as the waves pass. The heating is gentle, but pervasive. The balance between heating and cooling determines the thermal state of the cluster gas, which in turn affects how galaxies within the cluster can grow. If the gas cooled rapidly, it would condense into new stars at rates far higher than observed, producing galaxies much more massive and star-rich than we see. If the heating overwhelmed the cooling, the gas would expand and the cluster would become less bound. The observed conditions suggest a rough balance, with the sound waves maintaining equilibrium. This feedback loop represents one example of a broader phenomenon in which supermassive black holes regulate the growth of their host galaxies and the environments around them. The black hole grows by accreting gas, but its activity when it accretes, the jets, the bubbles, the sound waves, heats the gas and limits how much can fall in. The black hole is simultaneously enabled and constrained by its own behavior. The discovery that sound waves mediate this feedback was significant for models of galaxy evolution, which had struggled to explain how black holes influence gas on scales so much larger than themselves. The black hole at the center of Perseus is smaller than our solar system, yet its effects extend for millions of light years. The sound waves bridge this scale gap, carrying energy outward far more effectively than radiation or direct gravitational influence could manage. Other clusters show similar features, with central black holes producing jets and bubbles and, where the observations are deep enough, detectable sound waves. The Perseus cluster is not unique, but rather the clearest example of a phenomenon that appears widespread. The feedback mechanism discovered there seems to operate generally, though the details vary from system to system depending on the black hole's mass, activity level, and the properties of the surrounding gas. The universality of this process has implications for how we understand the evolution of structure in the universe. If black hole feedback operates in most massive systems, then the final state of these systems, their gas content, their stellar populations, their dynamical properties, reflects the integrated history of this feedback. The sound waves we detect in Perseus are not an isolated phenomenon, but a local example of something shaping cosmic evolution broadly. The efficiency of energy transfer from the black hole to the cluster gas can be estimated by comparing the mechanical power in the sound waves to the total luminosity of the black hole. The comparison suggests that a significant fraction of the black hole's energy output goes into mechanical work rather than radiation. The black hole is not just shining, it is actively working on its environment, doing the physical labor of moving gas and creating waves. The regions where the waves deposit their energy can be mapped by observing where the ripples are strongest and where they fade. The energy deposition is not uniform, but varies with distance from the center and with the local properties of the gas. Understanding this spatial distribution helps models predict how the cluster will evolve and what its future state will look like. The timescales of the feedback are important as well. The energy carried by sound waves produced 2 billion years ago is only now reaching certain parts of the cluster. The heating is not instantaneous, but delayed, with energy produced at one time affecting gas at a later time when the waves finally arrive. This delay means the cluster is never truly in equilibrium, but always adjusting to energy that was injected in the past. The scientific value of the Perseus sound waves extends beyond the specific system to general questions about energy transport in astrophysical plasmas. How energy moves through diffuse magnetized gas is a fundamental question with applications ranging from galaxy clusters to stellar coronae to laboratory fusion reactors. The sound waves provide a natural laboratory for studying this transport at scales and under conditions impossible to replicate on Earth. The detailed mapping of the waves also provides information about the properties of the cluster gas itself, because the propagation of sound depends on temperature, density, and composition. Variations in the wave pattern can reveal variations in the gas, allowing the cluster's three-dimensional structure to be inferred from the two-dimensional images. The sound becomes a probe of conditions it passes through. The continuing study of Perseus and similar systems benefits from improvements in X-ray observatories, with future missions promising even more detailed images that will reveal finer structure in the ripple patterns. The Athena mission, planned for the 2030s, will provide unprecedented sensitivity and resolution for studying hot gas in clusters. The sound from black holes will become even more clearly audible. The practical applications of understanding black hole feedback are admittedly limited. We cannot harness the energy of a supermassive black hole or reproduce its effects, but the scientific understanding has value in itself. Knowing how the universe works, how its largest structures evolve, how energy flows through cosmic systems, is part of the human project of making sense of our environment. The sound waves contribute to this project. The emotional and cultural significance of the discovery supplements its scientific value. Knowing that the universe contains sounds, that black holes sing across timescales of billions of years, that we have developed the ability to hear these cosmic voices, changes how people think about their relationship to the cosmos. The cold equations of energy transfer become warm with wonder when translated into sound. The feedback mechanism the waves reveal connects the very large to the very small, the supermassive black hole to the individual atoms in the cluster gas, the billions of years of wave propagation to the moments when the energy finally dissipates as heat. The sound spans these scales, carrying information and energy across distances and through times that dwarf human experience. The universe operates on principles that apply everywhere, and the sound waves demonstrate this unity. The Perseus black hole is not the only cosmic object that has been translated into sound, and NASA's sonification project has explored many other phenomena, each with its own acoustic character. The diversity of these translations reveals different aspects of astronomical data and reaches different audiences with different experiences. The Perseus black hole is not the only cosmic object that has been translated into sound, and NASA's sonification project has explored many other phenomena, each with its own acoustic character. The diversity of these translations reveals different aspects of astronomical data and reaches different audiences with different experiences. The universe, when converted to audio, becomes accessible in ways that visual data alone cannot achieve. Each object produces something distinct. The project began as an experiment in making astronomy more inclusive, allowing people who cannot see images to experience cosmic phenomena through hearing instead. But researchers quickly discovered that sonification offered more than accessibility. It revealed patterns that visual analysis sometimes missed. The human ear evolved to detect subtle variations in timing and frequency, skills that proved surprisingly useful for analyzing certain types of astronomical data. What started as outreach became a genuine scientific tool. The black hole at the center of the Milky Way, known as Sagittarius A star, has been sonified using data from the Chandra X-ray Observatory, the Hubble Space Telescope, and the Spitzer Infrared Observatory simultaneously. Each telescope observes different wavelengths of light, and in the sonification, each wavelength becomes a different instrument or voice. The X-ray data produces higher frequencies, while the infrared contributes lower tones, creating a layered soundscape that represents the chaotic environment around our galaxy's central black hole. The result sounds nothing like Perseus. It is more dynamic, more varied, reflecting the different scale and activity of the two objects. The Crab Nebula, the expanding remnant of a star that exploded nearly 1,000 years ago in a supernova visible from Earth in the year 1050-4, has also been translated into sound. The sonification maps the position of features in the image to stereo location, with sounds panning from left to right as the scan moves across the nebula. Different elements in the nebula, the filaments of gas, the pulsar at the center, the surrounding glow, produce different tones and textures. The spinning pulsar at the heart of the crab rotates 30 times per second, and this rhythm appears in the sonification as a rapid pulse underlying the slower movements of the expanding gas. Neutron stars, the collapsed cores left behind when massive stars die, have been sonified in ways that capture their almost unimaginable density and rotation rates. Some neutron stars spin hundreds of times per second, their radio emissions sweeping past Earth like lighthouse beams and producing rhythmic pulses that translate naturally into sound. These objects are called pulsars, and their regular beats have been converted to audio that sounds mechanical and precise, utterly different from the slow drone of the Perseus black hole. The comparison between the two reveals how different cosmic objects operate on vastly different timescales. The Eagle Nebula, famous for the Hubble image known as the Pillars of Creation, showing towering columns of gas where new stars are forming, has been sonified with musical tones assigned to different colors in the image. As an imaginary cursor scans across the pillars, the brightness and color at each position determine the pitch and volume of the sound produced. The result is something like abstract music, with melodic contours that follow the shapes of the gas columns. This approach differs from the Perseus sonification because the original data is visual rather than physical. The sound represents what the image looks like rather than any actual vibrations in the nebula. The distinction matters for understanding what sonification can reveal. When the Perseus black hole is sonified, the resulting sound represents actual pressure waves that exist in the physical universe, translated into frequencies humans can perceive. When the pillars of creation are sonified, the sound represents visual patterns being converted arbitrarily into audio. There is no physical sound in the nebula that corresponds to what we hear. Both approaches have value, but they reveal different things. The Perseus case is exceptional precisely because the underlying phenomenon is genuinely acoustic. Galaxy clusters beyond Perseus have also shown evidence of sound waves propagating through their hot gas, though none have received the same public attention as the original discovery. The Virgo cluster, much closer to Earth at about 50 million light-years, contains a central galaxy with a supermassive black hole that produces jets and bubbles similar to those in Perseus. The ripples in the Virgo cluster's gas have been detected and analyzed, revealing similar feedback processes operating across different environments. The phenomenon appears to be common in massive galaxy clusters. The frequency of these cosmic sound waves varies depending on the properties of the gas they travel through and the power of the black hole producing them. Some clusters show evidence of multiple frequencies overlapping, as if the black hole were producing chords rather than single notes. The analysis of these harmonics reveals information about the gas temperature, density, and the history of black hole activity over millions of years. Each cluster tells a slightly different story through its particular combination of waves. The emotional impact of sonification surprised many researchers who expected the public response to be mild curiosity rather than the intense fascination that actually emerged. When NASA released the Perseus audio in August of 2022, it spread across social media within hours, shared millions of times by people who found something genuinely affecting in the deep, sustained drone. Comments described the sound as haunting, lonely, ancient, terrifying, beautiful. Responses that scientific papers and images had never provoked. Something about hearing the black hole made it feel present in a way that seeing it never had. The audio triggered discussions about what it means to listen to something 240 million light-years away, whether the shifted frequencies preserve any meaningful connection to the original phenomenon, and why humans find certain sounds emotionally resonant, regardless of their origin. Philosophers and artists engaged with the recording alongside scientists, each bringing different frameworks for understanding what the sound represents. The simple act of translation opened conversations that pure astronomy rarely inspires. Musicians sampled the Perseus audio and incorporated it into compositions, using the black hole's note as a bass drone beneath other instruments. The recording appeared in ambient albums, electronic tracks, and experimental sound art, spreading the cosmic source into cultural contexts far removed from astrophysics journals. The black hole's voice, isolated and shifted and distributed, became a small part of human creative expression. The boundary between science and culture blurred. The accessibility dimension of sonification proved as significant as the emotional impact, with blind and visually impaired astronomy enthusiasts finally able to experience phenomena that had been described to them but never directly perceived. Workshops and educational programs began incorporating sonified data into curricula, allowing students to explore cosmic phenomena through multiple senses rather than vision alone. The universe became more inclusive, more available to people whose relationship to astronomy had previously been mediated entirely through others' descriptions. The scientific utility of sonification continues being explored, with researchers investigating whether certain patterns in data become more apparent when heard rather than seen. Time-varying phenomena like stellar oscillations and variable stars produce natural rhythms that the ear can track more easily than the eye scanning graphs. The detection of periodic signals buried in noisy data might be enhanced by listening rather than looking, though the technique remains experimental. Astronomers are gradually learning when sonification helps and when it merely entertains. The cultural phenomenon of space sounds has expanded beyond NASA's formal projects to include independent artists and scientists creating their own translations of cosmic data. Spacecraft transmissions, radio telescope recordings, and planetary measurements have all been converted to audio and shared online, creating an informal archive of cosmic sounds that continues growing. The boundary between official science communication and grassroots creativity has dissolved, with anyone possessing data and software able to produce their own versions of space music. The comparison between different sonification approaches reveals choices that affect what the final audio conveys. Some projects aim for literal translation, preserving as much of the original data structure as possible in the resulting sound. Others take artistic liberties, using cosmic data as inspiration for compositions that prioritize aesthetic experience over informational accuracy. The Perseus sonification falls toward the literal end, with the audio structure reflecting the actual geometry and frequency of the pressure waves, scaled but not fundamentally altered. The future of sonification in astronomy seems secure, with major observatories and space agencies increasingly incorporating audio translation into their public outreach and occasionally into their research practices. The success of the Perseus release demonstrated that substantial audiences exist for cosmic sounds. Audiences who might never read a scientific paper, but who will listen to a recording shared on social media. The translation of light into sound has become a permanent part of how astronomy communicates with the world. The Perseus black hole remains the most famous example because its sound is genuinely acoustic rather than merely derived from visual data, and because the emotional character of its deep, sustained note resonated with something in human psychology. The combination of scientific legitimacy and effective impact created a phenomenon that other sonifications have not matched. The black hole's scream became iconic in a way that graphs and images of the same data never did. The question of whether we are truly hearing the black hole or merely hearing a representation of data about the black hole invites philosophical reflection that most listeners happily skip. For practical purposes, the audio conveys real information about real physical processes occurring at an almost incomprehensible distance. The frequency may be shifted, the timescale compressed, the medium translated, but the underlying phenomenon, pressure waves in hot gas produced by energy from a supermassive black hole, is as real as any sound produced on Earth. The other sounds from space, diverse as they are, form a growing catalogue of cosmic audio that changes how people conceptualize the universe. Space is not the silent void of popular imagination, but a realm where different phenomena produce different signatures that can be translated into the language of sound. The silence between stars is real, but within galaxies and clusters, within nebulae and around black holes, vibrations propagate through whatever medium exists to carry them. The universe is noisier than we knew. The translation continues as new data arrives and new objects are selected for sonification. Each addition to the catalogue offers another voice, another character, another perspective on phenomena that visual astronomy alone cannot fully capture. The Perseus black hole's drone remains the deepest and most haunting, but it is no longer alone in the growing archive of sounds from beyond Earth. The telescope that made the Perseus discovery possible has been orbiting Earth for over 25 years, detecting high-energy radiation that ground-based instruments cannot see. The Chandra X-ray Observatory launched on July 23, 1999, carried into orbit by the Space Shuttle Columbia on a mission that deployed one of the most sophisticated scientific instruments ever built. The telescope was designed to operate for 5 years, but has continued far beyond that, still returning data that reshapes our understanding of the high-energy universe. X-rays are a form of light with much higher energy than visible light, produced by extremely hot gas, by particles accelerated to tremendous speeds, and by matter falling into the intense gravitational fields around black holes and neutron stars. Earth's atmosphere blocks X-rays from reaching the ground, which is fortunate for life, but inconvenient for astronomy. To see the X-ray universe, we must place telescopes in space above the protective blanket of air that shields us from this energetic radiation. Chandra was not the first X-ray observatory, but it achieved unprecedented resolution and sensitivity. The design of an X-ray telescope differs fundamentally from optical telescopes because X-rays do not reflect from mirrors the way visible light does. At normal angles of incidence, X-rays simply pass through or are absorbed by mirror surfaces. But at very shallow angles, almost parallel to the surface, X-rays can be deflected gently enough to be focused. Chandra uses nested cylindrical mirrors that guide incoming X-rays through grazing reflections onto detectors at the focal point. The mirrors must be extraordinarily smooth. Any imperfection would scatter the X-rays and blur the image. The resolution Chandra achieves is remarkable for an X-ray telescope, able to distinguish features separated by about half an arcsecond, roughly equivalent to reading a newspaper headline from half a mile away. This precision revealed details in X-ray sources that previous observatories had seen only as blurs, transforming points of light into complex structures with jets, bubbles, shock waves, and filaments. The Perseus cluster's sound waves became visible because Chandra's resolution could detect the subtle ripples in the hot gas, variations that cruder instruments would have averaged away into smoothness. The detectors at Chandra's focus measure not just the positions of incoming X-rays, but their individual energies, allowing scientists to create images at different wavelengths and to analyze the temperatures and compositions of X-ray sources. A single observation produces data that can be sliced into narrow energy bands, each revealing different aspects of the source. The hot gas in the Perseus cluster glows across a range of X-ray energies, and by analyzing how this emission varies spatially, researchers mapped the density variations that correspond to the pressure waves. The orbit Chandra follows takes it far from Earth, swinging out to nearly a third of the distance to the Moon before returning close to the planet. This elliptical path keeps the telescope above Earth's radiation belts for most of each orbit, minimizing the background noise that would otherwise contaminate observations. The orbital period is about 64 hours, during which the telescope can observe targets for extended periods without interruption from Earth's shadow or atmosphere. The long observations needed to detect faint features like the Perseus ripples would be impossible from lower orbits. The power for Chandra's instruments comes from solar panels that track the sun as the telescope orbits, providing electricity to run the detectors, the data recorders, and the communication systems that send observations back to Earth. The spacecraft also carries a system of reaction wheels and thrusters that point the telescope with extreme precision, holding targets steady during the long exposures that accumulate enough X-ray photons to produce meaningful images. Each pointing must be accurate to fractions of an arcsecond for the full resolution to be achieved. The data Chandra collects travels to Earth through NASA's Deep Space Network, the same system of large radio antennas that communicates with spacecraft throughout the solar system and beyond. The raw data is processed at the Chandra X-ray Center in Cambridge, Massachusetts, where automated pipelines calibrate the observations and produce images and spectra that scientists can analyze. The archive of Chandra data is publicly available, allowing researchers worldwide to search for phenomena in observations that the original observers might have missed. The longevity of Chandra has far exceeded initial expectations, with the telescope continuing to operate more than 5 times longer than its designed mission lifetime. Some degradation has occurred over the decades. Certain instruments have aged, and the amount of propellant for maneuvering has declined. But the core capabilities remain strong enough that NASA continues approving extended operations. The scientific productivity of the mission has grown over time as the archive deepened and as researchers developed new techniques for extracting information from the data. The discovery of sound waves in the Perseus cluster emerged from observations made in 2003, relatively early in Chandra's mission, when the telescope was still being explored for its full capabilities. The initial images showed structure in the cluster gas, but understanding what that structure meant required careful analysis and comparison with theoretical models. The realization that the ripples were pressure waves came gradually, as the spacing and properties of the features matched predictions for acoustic phenomena rather than other explanations. The 2003 study measured the wavelength of the ripples and calculated the frequency they implied, arriving at the extraordinary figure of 1 oscillation every 10 million years. This frequency corresponded to a note 57 octaves below middle C, far beneath any sound that exists on Earth and far beneath anything that could be directly perceived. The scientific paper reported these findings in the technical language of astrophysics, noting the implications for understanding how black holes regulate galaxy growth, but not emphasizing the acoustic interpretation that would later capture public imagination. Subsequent Chandra observations of Perseus added detail to the initial discovery, revealing multiple sets of ripples at different distances from the central black hole, corresponding to waves produced at different times in the past. The outermost ripples had traveled furthest and represented the oldest detectable sounds, while ripples closer to the center showed more recent activity. By comparing these features, researchers could reconstruct the history of the black hole's energy output over tens of millions of years, a timeline of cosmic screams preserved in the patterns of heated gas. The images that Chandra produces look nothing like photographs taken with visible light, appearing instead as fields of colored dots representing individual X-ray photons detected by the instruments. False colors are assigned to represent different energies or intensities, creating visual impressions that convey scientific information rather than natural appearance. The blue and purple hues often used for Chandra images indicate extremely hot gas at temperatures of millions of degrees, conditions utterly unlike anything familiar from everyday experience. The comparison between Chandra's view and optical or radio observations of the same objects reveals how different wavelengths illuminate different physical processes. The Perseus cluster, as seen in visible light, shows thousands of individual galaxies, but the hot gas that fills the space between them is invisible at optical wavelengths. Radio telescopes detect the jets from the central black hole, but not the broader ripples in the surrounding medium. Only X-rays reveal the hot gas and the pressure waves traveling through it. Each wavelength contributes a different chapter to the same story. The broader scientific impact of Chandra extends far beyond the Perseus discovery, encompassing thousands of observations of black holes, neutron stars, supernova, galaxies, and clusters throughout the observable universe. The telescope has revealed that supermassive black holes influence the evolution of their host galaxies in fundamental ways, that the hot gas in clusters contains most of the normal matter in the universe, and that high-energy processes shape cosmic structures from stellar to cosmological scales. The Perseus sound waves are one discovery among many, though perhaps the most publicly memorable. The future of X-ray astronomy will eventually require a successor to Chandra, as even the most carefully maintained telescope cannot operate forever. Several mission concepts have been proposed, including observatories with larger collecting areas and improved resolution that would reveal details currently beyond reach. The Lynx mission concept would have achieved order of magnitude improvements over Chandra, though it has not been selected for development. Whatever successor eventually flies will build on the foundation Chandra established. The operations team that has maintained Chandra for over 2 decades includes engineers and scientists who have devoted their careers to keeping the telescope functioning and productive. Some have worked on the mission since before launch, growing older alongside the spacecraft they tend. The institutional knowledge they carry cannot be easily transferred to documents, and their eventual retirement will represent a loss that goes beyond the inevitable degradation of hardware. Human expertise and mechanical capability have aged together. The telescope that revealed sound waves from a black hole 240 million light-years away continues orbiting Earth, still pointing at targets selected by astronomers worldwide, still detecting X-ray photons that carry information about the hottest and most energetic phenomena in the universe. The instrument has outlived predictions and continues surprising observers with what it can achieve. The discovery of cosmic sound waves was made possible by technology designed before the phenomenon was anticipated, a reminder that good instruments reveal more than their creators planned. The Chandra X-ray Observatory represents a triumph of engineering and scientific imagination. A machine designed to see invisible light from processes too energetic for Earth's surface. The telescope has operated through administrations, budgets, and priorities that have shifted many times, maintained by commitment that transcends any single decision. The X-ray universe it reveals remains as strange and fascinating as when the first photons reached the detectors a quarter century ago. The telescope watches while we sleep. The translation of cosmic data into sound raises questions about how humans understand phenomena that exist entirely outside normal sensory experience. The pressure waves in the Perseus cluster are real, but their frequency is so low that calling them sound requires accepting a definition based on physics rather than perception. No ear could detect them without translation, yet the translation preserves something essential about their nature. The question of what we are really hearing when we listen to the black hole invites reflection on how knowledge is constructed. Sound, in the everyday sense, refers to pressure waves in air or other media that stimulate the auditory system, producing the subjective experience of hearing. The definition relies on human perception as the standard, which makes sense for most purposes, but becomes problematic when discussing phenomena that operate at scales vastly different from human bodies. The pressure waves in Perseus behave exactly like sound waves in terms of physics. They are longitudinal oscillations in a medium, propagating at the local speed of sound, but they oscillate once every 10 million years rather than dozens or thousands of times per second. The shifting of frequency required to make the black hole's sound audible multiplies the original oscillations by factors of hundreds of quadrillions, compressing 10 million years of vibration into seconds. This transformation preserves the relative structure of the original waves, the peaks and troughs, the rising and falling, while changing the absolute values into a range humans can perceive. The question of whether the result counts as the same sound, or merely a representation of it, depends on what aspect of sound matters for the purposes at hand. The comparison to other forms of data translation might clarify what sonification accomplishes. When astronomers create false color images of X-ray or infrared sources, they assign colors arbitrarily to wavelengths that human eyes cannot see. The resulting pictures are informative and often beautiful, but no one claims they show what the objects actually look like. The colors are representations, not reproductions. Sonification operates similarly in some cases, assigning sounds to data that has no acoustic equivalent. But the Perseus case is different because the original phenomenon is genuinely acoustic in nature. The difference matters for understanding what sonification can teach. When the pillars of creation are sonified, the sounds represent visual patterns translated into audio through arbitrary mappings. The choices about which tones correspond to which colors are aesthetic rather than physical. When the Perseus black hole is sonified, the sounds represent actual pressure waves that exist in the physical universe, scaled to human perception but not invented from non-acoustic data. The translation is more literal in the second case, the connection to underlying reality, more direct. Whether this directness means we are truly hearing the black hole or merely hearing a processed version of data about it depends on philosophical positions about perception and representation that have no simple resolution. The pragmatic answer is that the sonification conveys accurate information about a real acoustic phenomenon, and that calling this hearing seems reasonable even if imperfect. The universe contains sounds too deep for ears, and technology allows us to experience something of their character, even if not their original form. The value of sonification extends beyond individual discoveries to encompass accessibility for people who experience the world primarily through hearing rather than vision. Astronomy has been a visual science since its origins, with telescopes designed to collect and focus light for eyes to see. People who cannot see have been largely excluded from direct engagement with astronomical data, relying on descriptions and translations that inevitably lose information. Sonification offers a path to more direct experience, even if the sounds are translations rather than original phenomena. The educational applications of sonification have expanded as the technique has become more widely known, and as tools for creating audio translations have become more accessible. Students can now explore cosmic data through listening exercises that complement traditional visual analysis, developing intuitions about patterns and variations that might otherwise require extensive graphical training to perceive. The combination of visual and auditory approaches may produce deeper understanding than either alone, engaging multiple cognitive systems in processing the same information. The research applications remain more speculative, with scientists still exploring whether sonification offers genuine analytical advantages or merely alternative presentations of findings that traditional methods reveal equally well. Some studies suggest that periodic signals and regular patterns become more detectable when heard rather than seen, potentially making sonification useful for identifying phenomena like stellar oscillations or orbital rhythms. Other applications remain to be developed as researchers experiment with different approaches to translating data into sound. The cultural dimension of sonification has grown alongside its scientific and educational uses, with the Perseus recording becoming a minor phenomenon in its own right. The sound has appeared in videos, podcasts, art installations, and musical compositions, spreading far beyond astronomy into broader creative culture. The black hole's voice has become a symbol of cosmic strangeness, a reminder that the universe operates at scales and in modes that human intuition cannot easily grasp. The translation made the phenomenon available for cultural appropriation in ways that data and images do not. The emotional response that the Perseus sound provoked in many listeners points towards something about human psychology that purely intellectual engagement does not reach. Hearing seems more immediate than seeing. In some respects, more visceral, more connected to bodily response. The deep tones of the black hole's translated voice evoke physical sensations alongside cognitive understanding, creating an experience that differs qualitatively from reading about the same phenomenon. The sound makes the discovery feel real in a way that numbers and images sometimes fail to achieve. The question of whether the universe is fundamentally amenable to human understanding takes on different character when considered through the lens of sonification. The fact that cosmic phenomena can be translated into experiences that move us emotionally might suggest that the universe and human minds share some deep structure. Or it might merely indicate that we are skilled at finding meaning in patterns, regardless of their origin. The philosophical implications remain underdeveloped, territory that future thinkers may explore more thoroughly. The limitations of sonification deserve acknowledgement, alongside its possibilities. Not all data translates meaningfully into sound, and some translations produce audio that is confusing rather than clarifying. The choices involved in any sonification, which data to include, how to map values to frequencies and timbres, how to structure the temporal flow, affect what the final audio reveals and conceals. There is no neutral translation, only choices that emphasize certain aspects of the data while obscuring others. The Perseus sonification itself involved decisions about how to scan the data spatially, how much to shift the frequency, and how to render the directional information as stereo audio. Different choices would have produced different sounds, each legitimately representing the same underlying phenomenon but emphasizing different aspects. The recording NASA released is one version among many possible, canonical only because of institutional authority rather than physical necessity. Other versions could reveal other features. The broader project of making the universe accessible through multiple senses continues as technology enables new forms of translation and as audiences demonstrate interest in experiencing cosmic phenomena in new ways. Virtual reality environments incorporate astronomical data into immersive experiences that engage sight, sound, and sometimes touch. The expansion of sensory channels through which the universe can be known represents a democratization of astronomy, opening fields that were previously accessible only to specialists with years of training in visual interpretation. The sound of the black hole persists in cultural memory, even as the initial excitement has faded, referenced in contexts ranging from science education to ambient music to philosophical discussion. The recording has become a touchstone, a shared reference point. for discussing the strangeness of the cosmos and the possibility of knowing things beyond direct experience. The translation from X-ray data to audio created something that has its own existence independent of the original phenomenon, a cultural artifact as well as a scientific result. The listening continues as new sonifications appear, and as audiences develop familiarity with the idea of cosmic sound. What seemed novel and surprising when the Perseus recording was released has become part of the landscape of space media. One more way that the universe is presented to publics who may never study astronomy formally. The normalization of sonification represents a shift in how astronomical communication works, adding audio to the traditional repertoire of images, graphs, and text. The knowing that listening provides differs from the knowing that visual analysis provides, engaging different cognitive faculties and producing different kinds of understanding. Neither is complete, neither is sufficient alone, and both contribute to a fuller grasp of phenomena that exist beyond human direct experience. The complementarity of sensory modes suggests that astronomy benefits from accessing all available channels rather than privileging any single sense. The universe exceeds any single mode of knowing. The black hole's sound endures as an example of what becomes possible when scientists and communicators collaborate to translate cosmic phenomena into human experience. The discovery was made by X-ray astronomers analyzing images, but the public impact came from audio specialists translating data into sound. The combination of expertise produced something neither group would have created alone. The result has become part of how humanity knows the universe in the early 21st century. The black hole at the center of the Perseus cluster has not fallen silent in the 2 billion years since the oldest detectable waves began their journey outward through the surrounding gas. The engines that produce the sound, infalling matter, accelerating jets, expanding bubbles, continue operating as they have since the black hole reached its current size billions of years ago. New waves are being generated at this moment, though they will not reach the edges of the cluster for millions of years and will not reach Earth for hundreds of millions more. The song continues. The gas that fills the Perseus cluster maintains temperatures of tens of millions of degrees, hot enough to emit the X-rays that Chandra detects, and hot enough to sustain the pressure waves that constitute the black hole's voice. This gas contains most of the normal matter in the cluster, far outweighing the visible galaxies that drift through it, like islands in a vast ocean. The medium that carries the sound is more substantial than the structures that produce light we might recognize. The invisible dominates the visible. The supermassive black hole itself remains hidden at the center of this system, its presence known only through its effects on the matter around it. Light cannot escape from within the event horizon, and even the material just outside it is so distant and so obscured by intervening gas that no telescope can image it directly. What we detect are consequences: the jets, the bubbles, the ripples, the heated gas. The source remains forever invisible, while its voice travels outward for billions of years. The timescale of the black hole's activity exceeds any comparison that human experience can make meaningful. 2 billion years ago, when the oldest detectable waves began their journey, the sun had not yet formed, and the atoms that would eventually compose Earth's crust were scattered through earlier generations of stars. The sound that Chandra detected has been traveling since before our solar system existed. carrying information about events that occurred when the universe was barely half its current age. The temporal depth is vertiginous. The energy required to sustain this acoustic output across billions of years exceeds the total output of most stars throughout their entire lifetimes. The black hole is not merely producing sound, but producing it at scales that dwarf ordinary astronomical phenomena. The power in the jets, the heat deposited in the gas, the mechanical work of expanding bubbles, all represent releases of gravitational energy as matter falls toward the event horizon. The feeding of the black hole produces the sound of the black hole, a cycle that has continued since long before Earth existed. The future of this system stretches forward as far as predictions can reliably extend, with the black hole continuing to accrete matter and produce energy for as long as fuel remains available. The gas in the cluster will eventually be depleted or will cool beyond the point where acoustic waves can propagate. But this depletion lies billions of years in the future. The black hole will continue singing for longer than complex life has existed on Earth. For longer than our planet will remain habitable. For longer than our sun will continue shining. The indifference of the phenomenon to human observation characterizes the entire cosmic landscape, but seems particularly stark when applied to something we have learned to hear. The black hole does not know it has been heard, does not care that its voice has traveled 240 million light-years to detectors orbiting a small planet in an undistinguished galaxy. The acoustic waves continue propagating, regardless of whether instruments exist to detect them or minds exist to interpret the detections. The universe operates according to physics, not audience. The connection between the listener and the phenomenon remains tenuous, despite the emotional impact that the sound produces in many who encounter it. We are separated from the black hole by distances that light itself requires hundreds of millions of years to cross, by physical conditions that would destroy any possible probe, by scales of energy and time that reduce human concerns to irrelevance. The sound creates an illusion of proximity that the reality of cosmic distance constantly undermines. We hear, but we cannot touch. The translation that makes hearing possible also introduces layers of mediation that separate us from the original phenomenon. The pressure waves in the cluster gas were detected as variations in X-ray brightness, converted to digital data, transmitted to Earth, processed through calibration pipelines, analyzed for structure, translated into audio frequencies, and finally rendered through speakers or headphones into vibrations in air that stimulate the auditory system. Each step involves choices and technologies that shape what finally reaches the ear. The connection is real but extended. The persistence of interest in the Perseus sound, years after its initial release, suggests that something about it resonates beyond novelty or momentary curiosity. The deep drone, the sustained quality, the association with vast timescales and incomprehensible energies. These elements combine into an experience that stays with people who encounter it. The sound has joined the small collection of cosmic images and facts that have achieved genuine cultural penetration, known beyond the boundaries of scientific communities. The darkness that surrounds the black hole extends outward to fill most of the universe, the vast spaces between galaxies where no matter exists to carry sound and where silence reigns completely. The Perseus cluster is an island of activity in this dark ocean, hot gas filling the gravitational well and providing the medium through which sound can travel. most of the universe is silent. The places where sound exists are exceptions that highlight the prevailing quiet. The night that surrounds you now, wherever you are listening, connects to that cosmic darkness through continuity of space that extends from the atmosphere above your location to the emptiness between galaxies. The air that carries sound to your ears is a thin layer wrapped around a small planet, itself a mote in a solar system, itself a point in a galaxy, itself a member of a local group dwarfed by the vast clusters where black holes sing. The scale increases faster than intuition can follow. The sound of the black hole continues whether anyone listens or not. A phenomenon sustained by physics rather than attention. The hot gas around Perseus will carry new waves outward tonight and tomorrow night, and every night for billions of years, the process operating with mechanical indifference to any observer. The scream is not a cry for help or a message intended for reception. It is simply what happens when energy flows through a medium capable of supporting pressure waves. The acoustic output is a byproduct, not a purpose. The knowledge that such sounds exist changes something about how the universe can be imagined, even for those who hear the recording only once and never think about it again. The cosmos is not the silent void that popular imagination often assumes, but a place where pressure waves propagate through the hot gas of galaxy clusters, where stars oscillate like bells ringing at frequencies that can be translated into audio, where the physics of sound extends far beyond the narrow range of human hearing. The universe sings, and we are learning to listen. The continuation of the search for cosmic sounds will add to the catalogue that Perseus began, revealing other voices from other sources across the vastness of space. Some will be translated from genuinely acoustic phenomena, pressure waves that exist in physical media between and around cosmic objects. Others will be sonifications of data that has no acoustic equivalent, creative translations that reveal patterns through audio, even though no sound exists at the source. Both types will contribute to an expanding sonic portrait of the universe. The rest that approaches, if rest approaches, comes in a universe where a black hole has been screaming for over 2 billion years and will continue for billions more. The sound is too deep to hear without translation, too distant to experience directly, too vast to comprehend through normal intuition. Yet it exists, verified by data from X-ray telescopes, analyzed by scientists who measured its frequency and calculated its power, translated by engineers who shifted it into the range of human perception. The scream is real. The Perseus cluster continues existing at this moment, hot gas filling the space between galaxies, pressure waves rippling outward from the central black hole, new sounds being born that will travel for ages before reaching the cluster's edge. The phenomenon does not pause for night or for rest, does not observe any cycle that human schedules might recognize. The black hole operates continuously, its voice sustained by the endless fall of matter toward the event horizon. The telescopes that monitor the X-ray sky continue operating as well. Chandra and other observatories gathering data that might reveal new acoustic phenomena in other clusters, other black holes, other concentrations of hot gas where pressure waves can propagate. The search is not concluded but ongoing, part of the larger effort to understand the high-energy universe through every available means. New discoveries await, though when they will come and what they will reveal cannot be predicted. The darkness between stars remains silent, the vacuum incapable of carrying sound, regardless of what energies might pass through it. The silence of space is real in the empty regions, even as sound exists in the filled ones. The contrast between silence and sound, between empty space and gas-filled clusters, characterizes the universe at large scales. Pockets of activity punctuate the prevailing quiet. Perseus is one such pocket. The black hole at the center of the Perseus cluster continues its song tonight. Pressure waves rippling outward through hot gas that will carry them for millions of years before they fade into the thermal noise of the cluster's edge. The sound began before Earth existed and will continue after Earth is gone, a duration that exceeds any human frame of reference. The scream persists. The translation that made this sound audible to human ears required instruments, analysis, creativity, and the recognition that acoustic phenomena can exist at scales vastly different from those we normally experience. The path from X-ray telescope to audiophile involved many steps, each necessary for the final result. The technology and the insight combined to produce something new, the ability to hear a black hole. The universe that contains this sound contains much else that remains unknown. Phenomena that future instruments may detect and future analysts may translate. The catalogue of cosmic sounds will grow as techniques improve and as data accumulates from sources not yet surveyed. Perseus was the beginning, not the end. The listening has just started. The night is quiet where you are, sounds of your own environment fading as attention drifts toward rest. The black hole's scream continues at a distance too great to matter for any practical purpose, in a medium too hot to survive, at a frequency too low to perceive without translation. Yet it is there, real as any sound you have ever heard, sustained for billions of years and continuing now. Rest comes in a universe where such things exist, where supermassive black holes pump energy into the gas around them and produce pressure waves that travel for ages through the hot medium of galaxy clusters. The strangeness of this reality does not diminish with repetition. It simply becomes part of the backdrop against which ordinary life proceeds. The cosmos operates according to physics that produces phenomena we have only begun to catalogue. Good night from the drowsy astronaut. Sleep well, and we'll explore the cosmos together again soon.